Welcome back to another Deep Dives. Today we're tackling a subject that, well, it's everywhere, but it often feels kind of complex, maybe even a bit intimidating. Electrical code. It's this foundational stuff that keeps things safe and running smoothly, in pretty much everything powered around us.
Okay, let's unpack this.
It's true. There's sometimes a bit of a phobia around electrical engineering. The concepts can seem abstract, but electricity, I mean, it's just fundamental to modern life, isn't it? Your phone, the grid, everything. Our goal today is really to make these basic concepts, the principles, and the way we analyze things much more accessible, cut through that complexity.
Right. And hello there, chap. This is going to be an extensive walkthrough of all the major aspects of electrical code, just as you asked. We've pulled together material from guides on the codes themselves, those detailed drawings, control systems, even how lighting design works. So maybe you're dealing with project specs, or you want to grasp industrial safety better, or maybe you're just curious. This deep dive, it's kind of a shortcut to feeling really well informed. Exactly. It might seem dense, but we're going to break it down, make it digestible, practical. We'll use analogies, talk about real-world relevance, trying to make sure the understanding really clicks.
The Foundation Understanding, the National Electrical Code, NEC.
Okay, let's start right at the foundation. The National Electrical Code, the NEC. For our audience, the question isn't really if we need codes, but maybe why this specific idea of a minimum safety standard from the NEC is so, well, crucial. It's more than just stopping big disasters.
Oh, much more. The NEC's main job, and it says this right in Article 90, is protecting people and property from electrical hazards. We're talking shocks, heat-causing fires or equipment damage, dealing with overcurrents, fault currents, all that dangerous stuff. It establishes a baseline, a minimum standard. It's not focused on convenience, really, or making future expansion easy. It's about a predictable, safe level. And, it aligns with international standards, too, like the IEC. Shows a global agreement on these basic safety ideas.
So it's not static. It's a living document, always changing. We're looking at the 2011 revision as our source, but how often does it actually change, and what does that mean for people working with it?
It gets revised every 3 years, which really highlights how fast electrical tech and our understanding of risk changes. While the core ideas grounding, overcurrent protection, things like that, they stick around, the specific article numbers, the detailed rules, they do change. So staying current isn't just, good practice. It's essential for safety. You have to keep learning. And for folks not deep in electrical work every day, the NEC handbook is often way more helpful. It's got tons of pictures, diagrams, examples, makes the dense code text much easier to grasp. It's kind of surprising how fast those revisions happen, actually.
That makes a lot of sense. Okay, before we get into specific applications, let's get our terms straight. Article 100, the definitions section, you mentioned it's really useful. What are some key terms in there where maybe the common understanding isn't quite right or the nuance is really important?
Good question. Let's pick a few that often have more depth than you might think. First up, ampacity. We know it's the max current a wire can handle continuously, but the key thing is ampacity isn't fixed. It's not just about the wire size. It changes based on insulation type, the temperature around it, how many wires are bundled together in a pipe, a raceway. So you always have to check the NEC tables, especially in Article 310, and apply these demurrating rules if conditions aren't perfect. It stops the wires from overheating. Critically important. Then there's bonding versus grounded. People mix these up all the time. Bonding is about physically connecting metal parts so they're all at the same electrical potential, like linking pipes and enclosures together. Grounding connects that whole bonded system to the earth or back to the power source. Bonding is a vital part of grounding, but you can't just use the earth itself as a bonding jumper. Its resistance is too high. Getting that distinction right ensures fault current takes the safe path back. How about continuous load? It's defined as a load running at max current for 3 hours or more, not counting startup. That 3-hour mark isn't random. It's why we use the 125% rule for sizing breakers and wires to handle that sustained heat buildup safely. And overcurrent versus overload. An overcurrent is any current above the rating. An overload is one type like a motor working too hard, which causes gradual overheating if it keeps going. But overcurrent also includes short circuits and ground faults. Those are sudden, huge surges of current. Very different. This affects what kind of protection you need and how fast it has to react. Lastly, voltage. Nominal, like 12240 volts. The insight here is that it's a label, classification. The actual voltage will fluctuate a bit, but it stays within a range where equipment should work okay. Understanding these details, that's where real code compliance starts.
That really clears things up. It's definitely in the details. So with those terms set, let's look at the wires themselves, the conductors. How do we size them? And what's the interplay between the material, the insulation, and, where they're installed?
Okay, conductor sizes. We use AWG American wire gauge for smaller wires, up to size 40, 4/0. Bigger than that, we use circular mills, now usually called case mill. A mill is just a thousandth of an inch, so the case mill is thousands of circular mills. It's just a way to measure the cross-sectional area. Now, the crucial part is Article 310 in the NEC. It covers everything: types, insulation, markings, strength, and most importantly, ampacity ratings. Table 310.15 specifically is probably one of the most referenced pages in the whole code book. It tells you how much current a wire can safely carry. These tables list ampacities based on copper or aluminum wire, and the temperature rating of the insulation, usually 60 degrees C, 75 degrees, or 90 degrees C. But, and this is critical, you have to adjust for the ambient temperature. If it's hotter than the standard 30 degrees C, which is about 86 degrees at CE, you must apply a correction factor, a debraiding factor. Let's make this concrete. Say you have a circuit needing 20 amps continuously. In a normal 30 degrees C room, an AWG TEG 12 copper wire with standard 60 degrees C insulation is rated for 20 amps. Looks good, right? But now, put that same circuit in an environment that's 50 degrees C, maybe a hot attic, or any of the machinery, that hashtag 12 wire. After you apply the derating factor from the tables, its safe ampacity drops way down, maybe to something like 11.6 amps.
Wow. So the exact same wire, carrying the same load, goes from perfectly fine to a major fire risk just because the room got hotter.
Precisely. That's the critical takeaway. To handle that 20 amp load safely at 50 degrees C, you can't use hashtag 12 anymore. You'd probably need to go up maybe even 2 sizes. An AWG ShagTag 10, DR-rated, might only get you about 17 amps. You'd likely need an AWG GTAG 8 wire, which, even after DR-rating, might give you around 23 amps. That's finally enough for the 20 amp load. It shows you can't just size wire based on the load alone. The environment is absolutely key and often forces you to use much larger wire.
That example really hits home. Okay, so we have the right size wire for the conditions. Now let's talk about the protectors, the overcurrent protection devices, OCPDs, breakers and fuses. How do they work, and what are the key rules for sizing them?
OCPDs, covered mainly in Article 240, are non-negotiable safety elements. They do 2 main things. First, protect the wires from getting too hot during sustained overloads, stopping insulation damage and potential fires. Second, they have to react instantly to massive short circuits or ground faults to protect equipment and people from, well, catastrophic events. The equipment also has a limit, a short circuit current rating, showing how much fault current it can take before it's damaged. Sizing them right is crucial. Article 210.20a has a key rule. For continuous loads, the OCPD rating must be at least 125% of that load. That extra 25% is a safety buffer for the heat that builds up over time. So if you have a 26 amp continuous load, you calculate 1.25 times 26, which is 32.5 amps. Then, according to Article 240.6a, you generally round up to the next standard OCPD size, which would be 35 amps. And importantly, that 125% factor also applies to the wire's required ampacity. The wire has to handle at least 32.5 amps too. It ensures the whole circuit is protected properly.
Right, that 125% factor is a built-in margin. Okay, rounding out this foundational part, grounding and bonding. We touched on the definitions, but Article 250, what's the big picture strategy there?
Article 250 is arguably one of the absolute cornerstones of electrical safety. It sets out the rules for grounding and bonding, not as nice-to-haves, but as essential safeguards. The main goal is to create a continuous low-resistance path for electricity throughout the system's metal parts, and critically, a reliable path for fault current to flow back to the source. Why? So if something goes wrong, say a live wire touches a metal motor casing, that fault current surges back, trips the breaker or blows the fuse quickly, and de-energizes the circuit before someone can get shocked or a fire can start. The key insight is that it's about directing dangerous energy safely. Without good grounding and bonding, that fault current might try to find another path, maybe through a person or through other equipment, causing damage. It's an engineered safety route for when things go wrong.
Beyond the basics, critical safety and installation standards.
Okay, moving beyond the core NEC rules, let's get into a specific and frankly, quite frightening hazard: arc flash. It sounds abstract, but the reality is devastating. Here's where it gets really interesting. What exactly is an arc flash? What makes it so incredibly dangerous?
Well, put simply, an arc flash is an uncontrolled electrical explosion. It's electricity arcing through the air, maybe phase to phase or phase ground, usually in systems over 120 volts. Imagine an industrial-scale welding arc, but completely out of control. NEC Article 110.16 requires warning labels about it, but the real detailed guidance comes from NFPA 70E, which, like the NEC, gets updated every 3 years. The energy release is just immense. Copper bus bars can vaporize, expanding something like 40,000 times their original volume in an instant. That creates a massive blast wave. Temperatures inside the arc plasma, they can reach around 5,000 degrees Fahrenheit. The total energy release, and incident energy, depends on voltage, the amount of fault current, and critically how long the arc lasts. Those huge fault currents, thousands of amps, are what drive the devastation.
5,000 degrees. That's hard to even imagine. What does that mean for a person caught nearby, and how often does this happen?
It's disturbingly common. Estimates are 5 to 10 arc flash incidents every day in the U.S. The human cost is just horrific. Medical costs alone can top $1.5 million for one incident. Total costs, including lawsuits and lost productivity, can easily hit $8 to $10 million. And OSHA, the Occupational Safety and Health Administration, takes enforcement very seriously.
So what does OSHA require companies to do to prevent this or mitigate the risk?
OSHA mandates a pretty robust 6-point compliance plan for facilities. 1, have a written active safety program. 2, calculate the potential arc flash hazard for all equipment 120 volts and up. 3, make sure proper warning labels are on the equipment. And here's a key point. It's the equipment owner's job to provide these labels, not the manufacturer. 4, provide the right personal protective equipment, the PPE, based on those hazard calculations, and make sure people use it. 5, train workers initially and then regularly on the hazards, how to read the labels, and how to use PPE and insulated tools safely. And 6, crucially, maintain the electrical equipment properly. Poor maintenance is a major cause of arc faults.
You mentioned the intense heat, but what other physical dangers are involved in an arc flash event? It sounds like more than just a burn risk.
Oh, absolutely. It's multifaceted and brutal. The extreme heat, yes, causes terrible burns, melts clothing. The brilliant flash, intense light that can damage retinas, cause blindness. High UV emission, like a severe sunburn, damaging skin. The shock wave, the arc blast itself, that explosive expansion of metal creates a pressure wave. It can throw people across rooms, break bones, collapse lungs. It's a physical explosion. Concussion from the noise, it's incredibly loud, requires hearing protection. Projectiles, bits of molten metal, or broken equipment flying like shrapnel. An electrical shock, because the explosion can expose live conductors. The danger doesn't necessarily end when the arc stops.
That's a horrifying list. So the PPE must be pretty specialized then, more than just, say, safety glasses and gloves.
Way more. The required PPE depends entirely on the calculated hazard level, which NFPA 70E classifies into hazard risk categories, or HRCs. For example, Category 0, low risk, up to 1.2 calories per square centimeter, might just need basic non-melting clothes, safety glasses, hearing protection. But jump to Category 4, high risk, 25 to 40 calcimeter, and you're looking at a full arc-rated suit system. Multiple layers, a hood, specialized gloves, hard hat, the works, everything rated for at least 40 calcimeters. And the labels are critical. They don't just say what PPE to wear, but sometimes they indicate if energized work is even allowed. If the potential energy is over 40 calcimeter, usually energized work is just flat out prohibited. Too dangerous.
Wow. Okay, so beyond wearing the right gear, the physical space around electrical equipment matters too, doesn't it? What do the codes say about that?
Yes, Article 110.26 is very clear. Access and working space shall be provided and maintained about all electrical equipment to permit ready and safe operation and maintenance. What that really means is you can't just stick electrical panels or switchgear in any old closet or tight corner. You need enough clear, unobstructed space around it so people can work safely, open doors fully, use tools, and get out quickly in an emergency. It's a fundamental safety requirement.
Makes sense. We got the rules, the hazards, the protective gear, the space. But how do we trust the equipment itself before it's installed? That's where those little labels come in, right? Certifications?
Exactly. Those labels, UL for Underwriters and Laboratories in the U.S., ETL from Intertech, NOM mark from Mexico, ULC for Canada, they're your proof. They mean the equipment has been tested by an independent lab and meets recognized safety standards when used correctly. Globally, you have the IEC, International Electrotechnical Commission, setting standards, and one really important IEC standard defines IP ratings ingress protection. That IP code, like IP67, tells you how well an enclosure protects against solids, like dust, the first digit, and liquids, water, the second digit. It's crucial for matching equipment to the environment. And this is where you see differences, say, between North American NEMA ratings and international IP ratings. A NEMA Type 4 enclosure is good against rain and hose spray. Its rough equivalent might be IP66. But if you need something truly submersible, say for a junction box in a tank, you'd look for NEMA 6 in the US or IP67 internationally. That 7 to in an IP67 means it's tested for immersion up to 1 meter. Understanding these codes is key for specifying equipment correctly, especially for international projects.
That's super practical. So we have safe equipment. Now let's look at the active devices that get built into systems to keep things safe moment by moment. What are some common examples in automated systems?
Yeah, this is where it gets interesting, seeing how different pieces work together. It's layers of protection. You have safety e-stop devices. These aren't just buttons. Often the contact block behind them is self-monitoring. If it falls off or gets disconnected, the circuit opens automatically. A nice fail-safe. Safety light curtains. These use invisible infrared beams. Break the beam, machine stops. Newer ones use communication networks like DeviceNet, which simplifies wiring immensely compared to the old point-to-point methods. Cable pull switches, like an e-stop on a rope, running along a conveyor, for instance. A really key safety feature is that you must reset them physically at the switch location. Forces the operator to check the area before restarting. Key interlock solenoid switches. These control access. You can't open a guard door until the hazardous motion inside stops, which releases the key. Ensures sequence safety. Guard mat safety mats. Step on the mat or roll equipment onto it and it detects the pressure. 2 internal metal sheets touch. The controller sees it and shuts down the machine. Safety PLCs. These are the brains for complex safety logic, replacing tangled webs of old safety relays. They look different, often red, and have redundant processors, constant self-checks, diagnostic features. They're designed to fail predictably and safely. And safety relays themselves. Even individual relays used in safety circuits are special, with redundant contacts and built-in diagnostics for higher reliability.
So how would these all come together? Say, in a typical robot cell in a factory.
Right, you'd see a combined strategy. There'd be a dedicated safety PLC, probably in a distinctly marked cabinet, maybe yellow. E-stop buttons would be easy to reach, maybe near openings. Limit switches might prevent a robot arm from swinging too far.
Right.
Trapped key interlocks on the main access doors. Cable pulls along any adjacent conveyors. Physical guarding, of course, to keep people out. And maybe even safety laser scanners creating invisible, protected zones that shut things down if someone enters. It's this integration, this layering of different technologies, mechanical, optical, electronic, programmable, that creates a really robust safety system, much more reliable than any single approach.
Blueprint to reality electrical drawings and logic.
Okay, we've talked about the components and safety devices. Now, how are these complex systems actually planned out and documented? Electrical drawings seem like the key language here, not just for building, but for fixing things later.
Absolutely. Electrical drawings are the essential roadmap. They communicate the design intent, the symbols, the conventions, and crucially, as you said, they are indispensable for troubleshooting. When a critical piece of equipment goes down, having accurate drawings is often the difference between a quick fix and hours of searching. They're vital in those triage situations.
Let's start with the simplest type, the one-line schematic or one-line drawing. What's its main purpose? Why just one line?
A one-line simplifies things, especially for three-phase power systems, by showing just one of the 3 phases. It assumes the other 2 phases are symmetrical, which they usually are. The big benefit is you can fit way more circuits onto a single drawing page. It gives you a quick, high-level overview of a large system at one glance. Really useful for understanding the overall architecture quickly, especially when you first walk up to a problem. You might see it used for an MCC, a motor control center. The drawing might label the main bus, 480V bus, 3, 4W, 600A, 60 Hz. That tells you voltage, phases, wires, amp rating, frequency. A horizontal line is the bus. Vertical lines dropping down are the individual motor starter buckets or branch circuits.
So if we zoom in on one of those vertical drops, say for a small 3-horsepower motor, what details would that one line show us?
It would show the sequence, typically disconnect switch, maybe with fuses inside it. Then the motor starter itself, often indicating an overload relay. And finally the motor. It would also specify the wiring and the conduit, something like 3/4 conduit, 3 1C shaft check 12, 1C check 12 grounded. That means 3 AWG check 12 phase conductors and 1 AWG check 12 ground wire inside a 3/4 inch conduit. Now, for an informed audience like yours, the real value isn't just reading that, it's thinking critically about it. Verifying those choices against the code. For that 3 HP motor, wire size. A 3 HP motor draws maybe 4.8 amps, FLA full load amps. NEC says size conductors for 125% of continuous load, so 6 amps minimum. AWG hashtag 14 wires okay for 6 amps, but notice the drawing specified AWG hashtag 12. Why? Often it's a company standard, a hard deck rule. Maybe they don't use anything smaller than hashtag 12 for power circuits, just for extra robustness. It's oversized, but safer. Ground wire. The ground carries fault current, not load current. NEC Article 250.122 might only require AWG hashtag 14 for this size motor, but again, they use hashtag 12 probably for consistency or extra fault capacity. Fuses, overcurrent protection. This gets tricky. NEC Article 430.52 sets maximum fuse sizes for motors to allow starting current without tripping, but still protect against shorts. For a 3 HP motor using time delay fuses, maybe 175% of FLA is allowed, so around 8.4A. You typically use a standard 10A fuse. But sometimes you see drawings where the specified fuse seems too large, like maybe a 125A fuse for a 40 HP motor. That calculation says should have a 100A max. Without a specific NEC exception noted, that could be a compliance issue, potentially compromising protection. It's a subtle but critical point.
Right. That's where design choices meet strict code limits. Are there other common mistakes or oversights you might spot on a one-line?
Yes, a really common one is forgetting the local disconnect switch right near the motor, especially if the motor is far away or out of sight from the main MCC, like a fan on the roof. NEC Article 430.102 generally requires a disconnect in sight from the motor location. There are exceptions, but having a lockable switch right there is a huge safety benefit for maintenance. Someone working on that fan can physically lock it out right there, ensuring it can't be started remotely from the MCC. It's a critical safety step sometimes overlooked.
That's a really important point for maintenance safety. Okay, so if one lines are the overview, wiring diagrams must be the nitty-gritty detail.
Exactly. A wiring diagram shows everything, all 3 phases, the neutral if used, the ground, control wiring, every single connection point. This level of detail is absolutely essential for building the panel correctly in the first place, and even more so for troubleshooting specific wiring faults later on. A key feature you'll see on wiring diagrams is unique wire labeling. Every piece of wire between 2 connection points gets its own label, like 1L1, T1, 2T2, etc. These aren't random. They follow a system. It's crucial for preventing miswiring during assembly and allows technicians to accurately trace circuits during maintenance or troubleshooting. Let's take a control circuit for a larger motor, say 75 HP. The wiring diagram would show the main 480 V power coming in, going through the disconnect and fuses. Then it would show the control power transformer stepping 480 V down to 120 V for the control logic. One side of that 120 V secondary is usually grounded, creating a neutral. That 120 V hot wire, often labeled X1, then goes through a control fuse, then typically through a normally closed STP button, then to the normally open start button. In parallel with the start button is a normally open holding contact from the motor starter coil, often labeled M. When you press start, it energizes coil M. Coil M closes its contacts, including that holding contact, which then keeps coil M energized even after you release the start button. It seals itself in. The circuit to coil M also usually includes normally closed overload contacts and any other required safety interlocks, like door switches, etc. If any of these open, coil M de-energizes and the motor stops. That basic start-stop seal-in logic is fundamental to most motor control.
That detailed step-by-step really clarifies how even a basic start-stop function relies on a precise sequence of contacts opening and closing. Okay, now let's pivot to the modern approach. PLCs, programmable logic controllers, how do they fit into control diagrams?
PLCs really changed the game. Instead of all those physical relays and wires for logic, you have a computer making decisions. The diagrams reflect this. You'll have an input control diagram. This shows how signals from the field sensors, push buttons, limit switches get connected to the PLC's input module. These are usually discrete signals, on or off. The input module takes the field voltage, like 120 VAC, and converts it into a low-voltage DC signal, maybe 5V or 24V, that the PLC's brain, the CPU, can understand as a digital 1 or 0. A key design practice here is fail-safe wiring. For safety devices, you often wire them so they're normally closed, providing a signal when things are okay. If the condition becomes unsafe, like pressure drops below minimum, the switch opens, the signal goes away, becomes 0, and the PLC knows something's wrong. The PLC scans all its inputs constantly, maybe every 20-30 milliseconds, so it sees these changes almost instantly. Then there's the output control diagram. This shows how the PLC CPU sends signals back out to the field. An output module takes the PLC's internal 1 or 0 command and converts it back into a voltage, like 115 VAC or 0 VAC, to turn things on or off, solenoid valves, motor starter coils, indicator lights, alarms. So if the PLC saw that pressure switch open, input goes to 0, its internal program might decide to turn on output #1 to start a backup pump motor, turn on output #5 to open a valve from a reserve tank, and turn on outputs #6 and #7 to activate an alarm light and horn. It's all programmed logic executing an automated response.
So the PLC is constantly scanning inputs, running its program, and changing outputs. But how is that program, that thinking, actually represented? It's not like writing code in C++, right?
Right, typically not. While programming software usually runs on a Windows PC nowadays, the most common language used inside the PLC is relay ladder logic, often just called ladder logic. It was designed deliberately to look like the old electrical relay wiring diagrams that electricians and technicians were already familiar with. It made the transition to PLCs much easier. It uses graphical symbols arranged in horizontal rungs, like rungs on a ladder. You have symbols representing inputs like examine if closed, XIC looks like a normally open contact, or examine if open, XIO looks like it's normally closed contact, and symbols representing outputs, looks like a relay coil. Power flows notionally from left to right across the rung. If all the input conditions on a rung are logically true, then the output coil on the right energizes. For example, controlling a fan. A rung might have an XIC contact for a master control relay, MCR, being on, an XIC for the start fan button being pressed, and an XIO for the stop fan button not being pressed. If all three are true, the output coil for cooling fan 3 energizes, turning the fan on. Often there's another rung using a contact from the fan output itself to bypass the start button, creating that seal-in or latching effect we talked about earlier. More complex logic uses timer blocks, counter blocks, math instructions. For instance, a timer might be used to delay the start of a second conveyor until the first one has been running for 2.5 seconds. When the timer's accumulated value reaches the preset value, like 2500 milliseconds, its done bit, the end, becomes true. And that done bit can then be used as an input condition on another rung to energize the second conveyor's output. It's a very visual way to represent logical sequences.
The bottom line, energy cost and efficiency.
We've covered safety, code, design, logic. That's a lot. Now let's shift gears and talk about how all this electrical knowledge impacts the budget, energy costs, and efficiency. It seems like it's more than just turning off lights, isn't it?
Oh, absolutely. If you really want to make a dent in electrical energy intensity, you need what some call a three-pronged approach. Many efforts only hit one or two.
Okay, intriguing. What are these three prongs?
All right, they are. 1, energy conservation. This is the one most people think of using high-efficiency stuff. Better motors, LED lighting, efficient HVAC, using less energy for the same output. 2, the supply side. This is about where your power comes from. Can you generate some power locally, maybe more cheaply? Think solar, cogeneration, taking control of the supply. 3, energy cost rate. This one's often missed. It's about digging into your electric bill, understanding the rate schedule, and optimizing your contract with the utility to get the absolute lowest price per kilowatt hour or per kilowatt of demand. Not just using less, but paying less for what you do use.
That last one sounds key. Utility bills can feel like a black box sometimes. How can someone, decode those complex rate schedules? What are the common parts?
They are definitely complex, but they usually follow a pattern. Let's take an industrial rate schedule, maybe like Duke Energy's OPTI, Optional Power Industrial Service Time of Use, as an example. You'll typically find a basic facilities charge, just a flat monthly fee for being connected. A demand charge. This is a big one for industrial users. It's based on your peak power usage during a specific interval, often 15 or 30 minutes, usually during on-peak hours. It can vary by season, summer, winter, and be tiered. The more peak power you draw, the higher the rate per kilowatt, kW. The key insight. You pay not just for how much energy kW you use over the month, but for your highest rate of usage at any one time. High peaks are expensive. Energy charges. This is the cost per kilowatt hour kilowatt consumed. But it's usually split drastically between on-peak and off-peak hours. On-peak, like weekday afternoons in summer, is much more expensive than off-peak. Nights, weekends, holidays. Shifting usage makes a huge difference, and often a power factor correction penalty. If your facility has a low power factor, often below 85% or 0.85, meaning you're drawing current inefficiently, common with lots of motors, the utility actually increases your bill demand charge. Poor power factor directly costs you money even if your kilowatt usage stays the same. Managing power factor is critical. Some utilities also offer an hourly pricing option, HP. This is for large users who can actively shift load based on predicted prices for the next day. Use more power when it's cheap overnight, cut back when it's expensive during a peak afternoon. Very sophisticated energy management.
Okay, so understanding those components, demand, time of use, power factor is key. Beyond just shifting load to off-peak, What other, maybe less obvious strategies can companies use to leverage these rates and cut costs?
There's some really smart plays available, often hidden in the rate schedule riders, like
Hmm.
on-site generation rider SG. If you have backup generators, you might be able to enroll them in a program where the utility pays you monthly credits just for making that capacity available to them during grid emergencies. You essentially get paid for the reliability you already have. It can even pay for the generator fuel used during testing. Or interruptible power service, Rider IS. Here, you agree to curtail a certain amount of your load if the utility calls an interruption event during peak times. In return, you get significant bill credits. It's a trade-off. Save money, but accept the possibility of having to reduce operations occasionally. The crucial thing here, though, is vigilance. The utility isn't obligated to tell you you're on the wrong rate schedule or that a better option exists. It's up to you, the consumer, to analyze your usage, talk to your account manager, and proactively seek the best rate, especially if your operations change significantly, like adding a big new machine or changing shift patterns. Look for flexibility. Can that energy-intensive process run off peak? Does owning your own substation transformers qualify you for a discount? Small details in the contract can mean big savings.
That's really empowering advice. Be proactive, know your contract. But what if a company sees these opportunities, maybe better lighting, a more efficient chiller, but just doesn't have the cash up front for the investment?
That's a very common scenario, and there's a specific solution. Energy performance contracting, or EPC. Usually this is done through specialized companies called energy service companies, or ESCOs. An EPC is basically a turnkey project to implement energy-saving measures. But here's the magic. The ESCO guarantees that the energy savings achieved by the project will be enough to cover the entire project cost, including financing, over a set term, often 10 plus years. So the company gets the upgrades essentially for free, paid for out of the savings generated, no capital outlay required. ESCOs handle everything: the initial energy audit, the design, installation, financing, commissioning, and importantly, the ongoing monitoring and verification, M&V, to prove the savings are actually happening. This model really took off because the guaranteed savings make it financeable. Banks are willing to lend against that guarantee. Because the ESCO's neck is on the line for the savings, they tend to stick to proven, reliable technologies, but the benefit for the client is huge. Major upgrades funded entirely by reduced operating costs.
That sounds like a fantastic model. So what kinds of specific electrical projects do ESCOs typically tackle to generate those guaranteed savings?
They focus on the measures with the best, most predictable paybacks. Things like lighting. This is almost always included. Huge savings potential, quick ROI. Replacing old tech like mercury vapor or old fluorescents with LEDs or modern high-efficiency fluorescents. Optimizing fixture placement and controls, HVAC, big energy user. Upgrading chillers, optimizing chilled water systems, variable speed drives on pumps and fans, better controls, sometimes even geothermal or solar thermal integration. Moving from manual controls to smart building management systems, BMCS, control systems, implementing advanced sensors, PLCs, and HMIs for tighter control over all building systems, minimizing waste. Code generation, CHP. Combined heat and power, generating electricity on-site and capturing the waste heat for process use, like steam or building heat. Much more efficient than buying power and making heat separately. Demand response. Implementing strategies or technologies that allow the facility to automatically reduce load during peak price periods or utility curtailment events. Even a small peak load reduction can yield big savings on demand charges. Renewable energy. Integrating solar panels, sometimes small wind or other renewables where it makes economic sense. Water and sewer conservation. Seems indirect, but pumping, treating, and distributing water uses a ton of electricity. Saving water saves energy. Sustainable materials. Less common in basic EPCs, but recognizing that the energy embedded in materials, extraction, transport, manufacturing, is significant. Using less material or recycled materials indirectly saves energy.
Illuminating insights, lighting system design.
That's a great overview of the broader energy picture. Now, let's zoom back in on one specific area you mentioned that's often a cornerstone of energy projects. Lighting. It's so visible, and it uses a lot of power.
It really is. Lighting upgrades often have such a good ROI and quick payback that they help make the business case for the whole energy project. They can sort of fund the longer payback items. Organizations like ISNA, the Illuminating Engineering Society, and the International ICI set the standards here, focusing on getting the right amount and quality of light efficiently.
Okay, so to talk about lighting design properly, we need the right vocabulary. What are the key terms we need to understand?
Let's hit the main ones for practical design. Luminous flex. Think of this as the total amount of light coming out of a lamp or fixture, measured in lumens. LM. More lumens means more light overall. Luminous intensity, this is about how bright the light is in a specific direction. Measured in candelas, CD. A spotlight has high luminous intensity in its beam. Illuminance E, this is the one we usually care about for tasks, is the amount of light landing on a surface, like your desk. Measured in lux, LX internationally, or foot candles, FTC, in the US. 1 lux is 1 lumen spread over 1 square meter. An example helps. Imagine a tiny light source emitting just 2 lumens in all directions. Right next to it, it might seem bright, but 5 meters away. The illuminance, the light actually hitting a surface there, would be incredibly low, maybe 0.0064 lux. Light spreads out fast. This leads to luminous efficacy, or S. This is simply lumens out divided by watts in LMWA. It tells you how efficiently a light source converts electricity into visible light. Critical for comparing different technologies, LEDs might be over 100 mmW, while an old incandescent was maybe 15 mmW. Big difference in energy use.
Okay, lumens for total light, candelas for directional brightness, lux or foot candles for light on the task, and efficacy for efficiency. Got it. But how much light, how many lux or foot candles do we actually need? It must vary, right?
Absolutely varies. You don't need the same light level in a hallway as you do for intricate assembly work. The IE publishes detailed recommendations, usually in tables, with categories from A, simple orientation, to I, very difficult visual tasks. But here's the key insight. They provide a range for each category. Picking the right level within that range depends on weighting factors. Mainly, the age of the people using the space. Older eyes generally need more light. The importance of speed and accuracy for the task being performed, and the reflectance of the surfaces in the room and the task itself. Dark surfaces soak up light, requiring more initial output. So you assess these factors, get a weighting score, and that tells you whether to use the low, middle, or high end of the recommended illuminance range for that task category. A lobby, category C, with older occupants might need 150 lux, while that watchmaker doing highly critical work, category G, might need 5,000 lux or more. It's about tailoring the light to the specific human and task needs.
That's a really nuanced approach, very human-centric. Okay, beyond the source and the target levels, what about the physics of how light travels and interacts with surfaces?
Right, there are a few fundamental laws governing this. Lambert's law, or the cosine law. This basically says that if light hits a surface at an angle, the illuminance is reduced by the cosine of that angle. Imagine shining a flashlight straight down versus at an angle, the angled light spreads over a larger area, so it's less intense at any given point. The illuminance inverse square law, this is the big one. Illuminance decreases with the square of the distance from the source. Double the distance, you only get 1/4 the light level. This is why a light high up in a warehouse needs to be incredibly powerful compared to a desk lamp right next to you. If a light gives 900 lux at 1 meter, the inverse square law tells you it's only about 43 lux way out at 4.57 meters. Distance matters, hugely. And the illuminance cosine cubed law, this just combines the first two. It accounts for both the distance inverse square and the angle cosine effect, showing how light drops off even more rapidly when it's hitting a surface far away and at an angle from the source.
Okay, so those laws tell us how light diminishes with distance and angle. How do designers put all this together, the terms, the target levels, the physics, to actually design a functional lighting system?
Good question. It's a synthesis. They consider the source type, the task needs, whether direct or indirect light is better, and increasingly how to incorporate daylighting. Design with daylight is powerful for saving energy, but tricky because sunlight varies so much. Methods like the daylight factor, DF, try to predict indoor light levels based on the available light from the sky and reflections. For artificial lighting, a very common practical method is the lumen method, also called the zonal cavity method. It starts with the total lumens produced by the fixtures you plan to use, but then crucially it applies 2 reduction factors. 1, the coefficients of utilization, CU. This number, less than 1.0, represents how efficiently the light from the fixture actually makes it to the work surface, considering the fixture's design, the room shape and size, cavity ratio, and how reflective the walls, ceiling, and floor are. 2, the light loss factor, LLF. This accounts for the fact that light output decreases over time. Lamps get dimmer as they age, and dirt builds up on lamps and fixtures, blocking light. The LLF accounts for this depreciation. So you calculate or look up the CU and LLF for your specific room and fixtures. Multiply the initial lamp lumens by these factors, and divide by the area to estimate the maintained luminance, the average light level you can expect over the life of the system, accounting for all these real-world losses. This ensures you install enough light initially to still meet the target levels, even after degradation. It's about designing for long-term performance, not just day-one brightness. Outro.
Wow. That was truly an extensive walkthrough. We've gone from the absolute basics of the National Electrical Code definitions, safety principles, all the way through arc flash hazards, safety devices, the different kinds of electrical drawings, PLC logic, the whole world of energy costs and utility rates, ESCOs, and finally into the science and art of lighting design.
It really covers a lot of ground, doesn't it? But the key takeaway, I think, is that understanding these things isn't just for electrical engineers. It really empowers you to make smarter decisions, to ask better questions, to see safety hazards you might have missed, and find those opportunities for efficiency, whether it's at home, at work, or in a big industrial plant. The complexity, when you break it down like this, actually reveals a very logical, very protective system designed to manage electricity safely.
It absolutely does. It feels much less like a mysterious black box now. So, as we wrap up this deep dive, here's a final thought to leave you with. We see technology advancing so rapidly: smart homes, AI in manufacturing, incredibly complex automation. How do you think our electrical codes, which we've seen are already constantly evolving, will need to adapt even faster to keep up with this innovation while still holding on to those fundamental safety principles we spent today discussing?
That's a great question and a critical challenge for the industry. And hopefully after today, you, our listener, will look at things a bit differently. Pay attention to those warning labels on equipment. Glance at the demand charges on your electricity bill. Notice the type of light bulbs being used. Recognize that behind all of it is this intricate system of codes, engineering design, and safety considerations we've explored today, all working, mostly unseen, to power our world safely and reliably. You're now equipped to see that hidden layer a little more clearly.